get you to understand a little bit what magnetism is. Once I'm done that, this part should only take me about half an hour, maybe not even, maybe like plus or minus 5 minutes, let's say. And then once I'm done that, I'm going to give you guys the rest of the period to work on circuits and building circuits, measuring stuff with your circuits, or practicing problems. So this is kind of like your preparation period for the lab test and for the theoretical test. Next week, I have some review problems that we can go over in class, but it's only going to be, I only have 4 questions or so of review. So it's not going to be a full 2.5 hour review period or anything like that. It'll be maybe an hour or so. And beyond that, though, we're moving on into magnetism and things like that. And this part is not going to be on the test, nor on the lab test, nor on the theoretical test. Everything from magnetism and beyond is only going to be tested on the final exam. The final exam, as you know, is cumulative, right? So it's everything from the beginning of the year. All right. So let's get started. This is PowerPoint number 20. And it's quite interesting, magnetism. It's not, it's a little bit more abstract than the other 2 topics that we've done. Circuits are very concrete, like you know where the current is going, you can see things happen. Here, you kind of just have to take my word for a few things. And if you do that, then it should be easy. And then if you go on into, anyone here interested in going into electrical engineering? Maybe? Okay. It's really interesting, and it's high in demand. It's one of the hardest engineering, I think it's the hardest engineering program to get into at this point. It's also the hardest to do, not just to get into. But it is quite interesting, and there's a huge demand for it. Magnetism plays into this quite a bit because, as you know, magnets are used to create electricity. So everything that we have, all this power that we have here, at least in Quebec, or anywhere that's powered by anything that's based on a turbine, is powered by magnets. All right, so Hydro Quebec, all their turbines are powered by magnets, and we get electricity because of magnets. So it's quite important. It's one of the 4 fundamental forces, right? And that's really, really, really cool because it's only the second one that you've learned out of the 4. The first one being gravity, the second one being magnetism. The third and fourth ones, it's not electrostatic forces or anything else. It's something called strong interactions and weak interactions. And these strong interactions and weak interactions, they encompass globally the idea of electrostatic forces, but it has to do more with like relativistic physics and things like Planck's and radioactive decay. So we won't talk about those 2 other ones, but this is the second one. We're going to talk today about sketching those magnetic field lines. All right, so we did electric field lines. Today we're going to do magnetic field lines. It's a very similar process. And I just wanted to draw this parallel for you. Okay, so on this slide, you see that there is a force, and we're going to name the force in this column here. So we have either gravity as a force, electrostatics as a force, and magnetism as a force. And they each act on different things. So gravity acts on something that has a mass, and electrostatic force acts on something that has a charge, while magnetic force acts on anything that might be polar or has poles. And just like we have, if you place an object in a place of gravitational field, it'll feel a gravitational force. If you place a charge in a place of electric field, you're going to feel electric force. And if you place something that has a pole in a magnetic field, it's going to feel a magnetic force. Okay? So it's kind of redundant. It's very similar. The only thing that's going to be different is the direction, right? And we'll talk about that with the right-hand rule. Do you guys remember the right-hand rule? You're sitting in grade 10 and sit on that cat and you're like, there's always that one kid who's using his left hand and you're like, oh, poor kid. Is that you? Magnets are hugely important. All right, they're literally everywhere. Like I said, all the electricity that's being generated is because of magnets. Everything that makes sound is because of magnets. As you know, speakers are gigantic or small magnets, depending if they're big speakers or small speakers, that are moving up and down to vibrate air molecules, right? So you produce sound that way. Here's a list of stuff that uses magnets. I mean, most of these are just things that make sound. But there are other things as well. And if you're more interested in this topic, I'm not getting into these topics, but if you are interested in them, look up these subjects here. They're quite interesting. There's a lot to apply to everything that we do in terms of magnets. Oh yeah, I have a slide that for some reason takes really long to load, and now I'm pretty sure I skipped over it. So yeah, I'm gonna have to go back and I have to wait again. I don't know why it takes so long to load this slide. I think it's just an image or something. There you go. So in order to understand magnetic force, you have to first understand magnetic field, right? So remember, a field is where there is going to be a magnetic force if you place a pole object in. And a magnetic field is measured in this unit. Come on, pen. Okay, it's not writing. It's measured in this unit T, which stands for Tesla. All right, that's the unit for it. The variable for it, and it's not written here, and I would like you guys to write it, and I would write it if I could make my slide work. The symbol for magnetic field is B, and it's a vector. Okay. So I'm showing it here. Magnetic field is equal to B, and it's measured in Tesla. Okay. You can measure them in Gausses, but we never do that. I'm not even going to bother showing you the conversion. But essentially, it's another common way of measuring it. And then we have to talk about things that are something called a bar magnet. And a bar magnet is what you're used to seeing is that this is considered to be a bar magnet, or this is considered to be a bar magnet. And what this is that it's a magnet that has two poles to it, a north pole and a south pole. There's other things that have north poles and south poles, such as our planet, but we'll get into that. And if these objects, if a bar magnet comes into contact with a non-magnetic object, it has the ability to create a magnetic object from a non-magnetic object. So have you ever seen where you take a magnet and you touch a paper clip, and then that paper clip becomes magnetized, and you can pick up another one, and then you can pick up, and then you have like a string of paper clips hanging from the magnet? Well, that's because that magnet, that bar magnet, magnetized those paper clips, and that paper clip magnetized the next paper clip, and that, and so on and so forth. And the idea behind a bar magnet is that it's considered to be a permanent magnet in the sense that it doesn't need to be magnetized in order for it to be magnetic, right? So that paper clip on its own is not magnetized. It's not magnetic unless it's been magnetized by a magnet. I've been saying magnet a lot. And so by convention, we have the idea that the magnetic field lines leave the north and enter the south. Kind of like by convention with the electric field, it was leave the positive and into the negative. In magnetism, it's leave the north and enter the south. So I'm gonna ask you guys later to draw some magnetic field lines for me, and you're gonna have to do it from the north into the south. So here on the left, you'll see something I mentioned just before, was this concept of permanent magnets. And permanent magnets, like I said, is something that's always going to be producing a magnetic field, regardless if there's a magnet nearby it or not. So it is just a magnet, all right? And I also mentioned that a current, or we also talked about how Hydro-Quebec is giving us electricity through these currents. And the way they're doing that is by like if a current goes through, if a current moves, it produces a magnetic field. All right, so what Hydro-Quebec has done is they did the opposite. So they put a magnetic field through a wire, and then the movement of the magnet through the wire produces a current in the wire, and that current is what we're getting over here. It's going to be an AC current, and at the end of this topic, we're going to be getting to how that works exactly. And also, of course, our planet It's a humongous magnet, right? It's not a very strong magnet, but it's a pretty good magnet. So again, the rules here are for drawing magnetic field lines is that they leave the north and they enter the south. Okay, and anywhere that's magnetic, anywhere that's like in this case, this is all of the red part is considered to be the north part of the magnet. So the magnetic field lines will be leaving everywhere along that north part of the magnet and entering everywhere all along that south part of the magnet. And a good way to remember this, actually no, that's not a good way to remember this at all. It's the total opposite of what you would think intuitively. If I were to hold a compass, the north end of my compass is going to be pointing to the magnetic south pole. Okay? So if I had a compass right here, anyone play with compasses before? I'm just assuming that everyone's used a compass. Yeah? Okay. So the compass, it's the red arrow that points towards the north, right? And that's silly because it's actually pointing towards the south, right? And I'll explain to you why we have this convention. What's that? Exactly, yeah. So I have this diagram, and this diagram is a picture of our planet, and there's something wrong with this picture. It's totally wrong. Now, what the severity of the incorrectness of this lies in where it's published. This picture used to be published on a NASA website, and you can't have NASA website being wrong about things like this. But just to tell you that it's a very common mistake and that I don't want you to fall into this trap. I said that the field lines leave north and enter south, right? And therefore, that means that if I were to just follow the field lines here, the magnetic north is down there, and the magnetic south is up there. And that's true. The magnetic north is down there, and the magnetic south is up there, except on the websites, they reversed the labels. So you'd have to change these. And this is the magnetic south. I'm going to call it S sub M, and M sub M for magnetic north, magnetic south. And it's the opposite of geographic north and geographic south. Okay, so if I put a compass here, it's going to be pointing northwards, and that's great because it's pointing to magnetic south. Yeah. It's going to be pointing to the geographic north or the magnetic south. The geographic north is just where north is, where north we actually call north. And the magnetic one is where the south end of our planet's dipole. And as you can see here, and this part of this diagram is accurate, the north, the geographic north, and the magnetic south are not exactly located one on top of each other. There's an 11.5 degree separation between the two. Okay? So this is what it is in reality. This is the right answer. So this is, we're going to call this magnetic south. And we're going to call this geographic north. And it's the opposite for the bottom. Okay? They're not exactly on top of each other. They're quite far. But imagine that you're in the Renaissance age and you're navigating the seas. Knowing where north is based on a compass is good. It's important. And if it's off by a little bit, it's not that bad. And what's great is that it's always consistently pointing in the same direction. So it's a great point out of that. It's always like, okay, that's that direction I need to be going. It's quite important. That discovery was very, very important. So talking about compasses, I had this question for you. So I have a charged rod, right? And the rod has got positive charges on it. and I have a compass standing right. This compass, is it going to continue pointing north? Is it going to point towards the positive charge rock, or is it going to point away from the positive charge? What do you guys think? Which one? Not at all. Why? Exactly. You have to remember that the electric field provides an electric force on poles, not on charges. So the answer with this would be not moving at all. Okay? If the charges were moving, as in a current, then yes, you would have a magnetic force. But in this case, this is a static electric situation, and therefore there is no force. Okay? So this is static electric, static, and therefore no force. No magnetic force. Pardon? C'est pas magnétique. It's, it's always magnetic, right? But it's always pointing to the magnetic south, which is located near the geographic north. So it's pointing north, it's pointing to geographic north, but in reality, what it's doing is pointing to magnetic south. All compasses are magnetic. There is no geographic compass. Which one of these are is correct? So I'll just outline some of the differences. The first one here, the magnet is connected to the north end of the paper clip, which is connected to the south end, and the south end now is doing opposite attract situation. All right, here it's opposites always, and here it's similars always. So which one of these is correct? I'll give you a hint. It's like electrostatic forces. Yeah? B, absolutely, because the opposites attract. So in no situations should you have that there is a force, an attractive force between two similar poles. Okay, so it's opposites attract, or opposite poles attract each other. Okay. All right, here's what I want you guys to do. I want you to reproduce these little diagrams in your notes and try to draw the field lines. Try as many as you can. Once you're done, we'll do some on the board. Take, I don't know, 5 minutes to do this. as you might have imagined, magnetic field lines cannot cross. So I cannot have two different magnetic fields at any one given moment. It's the same rule that we had for electric fields. Something like that. So if I were to put a object with a pole in there, in any of its fields, then it would follow the field line. If I put something with a north pole and I put it here, it's going to go it's going to go with the field lines. If I put something with the south pole here, it's going to go against the field lines. Very, very, very similar to what we were talking about in an electric field line. Okay? You guys remember that? It's been a long while now, but it's okay. So we talked about the planet and how the planet has a magnetic field. And the planet actually acts as a bar magnet or a permanent magnet. And it always has this kind of dipole moment. And, um, and the question is, how is it that our planet could produce a magnetic field? And the answer to that is quite interesting. There is, you guys know what convection currents are? Have you guys heard of that before? Convection currents are currents, whether they're liquid or gaseous, but currents created by a difference in temperature, right? So we have at the very core of our planet a really hot core, and over that we have a cool mantle. So you have a big, huge temperature difference, and using these huge temperature differences, the liquid inside or in between the core and the mantle is going to flow in a convection kind of way. And I said to you guys before that anything that's a charge doesn't create a magnetic field, but anything that's a moving charge does. And that's exactly it. So this is ferromagnetic liquid that's being moved in between the core and the mantle. So this ferromagnetic liquid contains a charge, and this charge moving up and down inside the cores in the Earth's core is producing a magnetic field around the entire planet. All right, and it's quite useful. You guys know why we need to have a magnetic field on our planet? If we didn't, I don't think that life could exist on our planet. That's how important I think it is. So why? Why do you think that our Earth having a magnetic field is so important? It contributes to gravity because it's a very dense metal, and a dense metal means that our core is heavier, creating a gravitational force. But it's not the magnetic part that makes that important. That's just the material. So what is a magnet important for? Have you guys ever heard of solar flares? So the sun actually has these bursts of solar energy that are very, very, very rich in high energy electromagnetic radiation, which is a cancer causing thing. And in fact, the rays are so strong um, that they would actually just kill us. They wouldn't necessarily give us cancer in the long term. They would just kill us straight up. And and our magnetic field, which extends about 400,000 kilometers outside of our planet, like that's a huge radius, right? So about 400,000 kilometers outside, there's this enormous magnetic field around our planet that's protecting us from any kind of electromagnetic radiation coming in from the sun. We still get some, and a lot of it is getting blocked off by the atmosphere. And even then, it's still dangerous for us to sit outside with no sunscreen on, right? So a lot of it is getting filtered by our electromagnetic field, or sorry, our magnetic field. Then the rest is by the atmosphere, and then we have trace amounts of this radiation left over that we need to protect ourselves against. And that even that we consider to be dangerous. So imagine if we didn't have it. It's also responsible, these convection currents and all this stuff are responsible for our topography. I won't get too much into that. But I will get into just really quickly on how our magnetic field reverses every few years. And reversal is reversal, so that you do between the north being south and then flipping over to the other way. And it used to, it would happen around like every 5 million years, and now it's more and more frequently. And every time it happens, they're predicting that it's going to take less and less time. And so they're saying that it's going to be 2 years before the next magnetic flip. And that's quite recent. Now, I don't know what the health repercussions are, because I know that that's always the first question is, oh my God, the magnetic field is going to flip. Does that mean we're all going to die? No, it doesn't mean we're all going to die, because it's happened a lot, and it didn't kill all the organisms on the planet. But it does have an effect on how we might be affected by solar rays during that time. Yeah. Exactly. So what happens is the poles will switch where the magnetic south will become the magnetic north and vice versa. Yeah. Okay. Very interesting question. I'm going to get straight to this diagram. So here is a diagram representing the magnetic field and its behavior as a function of time. So just the orientation of the field lines and the fact that it moves gives them an indication that it's done so. And then we also have um, artifact artifact evidence that it has already flipped in the past many times. So there's two evidences, and this is a model showing how it will reverse, or it's mid-reversal on the left, and then further in the reversal on the right. But they have this kind of data from the past. Not nearly as impressive as this thing. There are places on the planet, obviously, that have a stronger magnetic field than others. And based on this diagram, what conclusion can you make about where is the strongest magnetic field? The poles, yeah, closer to the poles. All right. But we're not talking about a very strong magnetic field. We're talking about up to 60 microtesla, which is like the highest that you'll get if you were standing right on top of the magnetic poles. But is that a dangerous amount? 60 microtesla. No. Anyone here had an MRI before? Yeah, we're talking about like kilotesla. Those magnetic and those MRI machines. So no, they're not very dangerous at all. It's just the strength of the magnet. And you guys have obviously heard of migratory animals, right? So animals that can detect when the weather is changing, they know to go south. Why don't they go north when it gets cold? Well, the reason for that is because in their vestibular system, they have ferromagnetic liquid, and it is giving them an indication as to which direction south is based on the magnetic south and the magnetic north. Is that interesting? What's that? In their vestibular system. So you know we have like these semicircular canals that allow us to detect head motion. They have it. It's different for them. It's ferromagnetic. Yeah. Yeah. They would mess them up a little bit. Yeah. So sea turtles have this, deer have this, and like duck and geese and all these things have it as well. I'm going to stop there. Let's take a 5-minute break, and then when you come back, just don't even wait for me to say anything. Go straight into the, oh, actually, right before I get started, the lab test is going to be 13 stations. All right, two of those stations are going to be break stations. There you go. There's nothing for you to do there. It's for you to catch up on other questions or just relax if you're feeling stressing out or whatever. There are questions. There's a range of difficulty of questions. So there are some that you're going to get there and you're like, done. It'll be done in 30 seconds, and you'll have to just wait there until the next rotation. Each station is 10 minutes long. So if you're done in 30 seconds, you're just sitting there for 9 minutes and 30 seconds. So it's going to be something you're going to be doing moving, some that you're going to be scrambling to do it fast enough in order to not lose time. I recommend that you try and do it as fast as possible, just so you don't give yourself trying to finish the last second. And if you have something that's difficult, just write down. What's important is that you take down all the right measurements. Once you take down the right measurements, you can get another station that you've done early, and you can go back to a question and say, oh yeah, okay, I can calculate this now that I have the measurements, I have some free time, or you can do that at the break station or whatever. The break station are strategically placed so that they're right after long stations, the ones that take more time. So those of you who start on the station right before the break, and you're like, oh crap, that sucks because the next station is the break station. I'm not going to have anything to catch up on. Well, no, that break station is placed there strategically so that it's right after the long one. Now, if you start on the break, that really sucks. The only change for you is that you're going to have one extra break at the end. Okay, so you're going to do the whole thing, and when everyone's done, you're going to have an extra break. It's 10 minutes per station, and it's 13 stations, so that's 130 minutes, or 2 hours and 10 minutes. Um, After that, you're done. Okay, so there's no extra time after that, unless you're the one who started on a break station, at which point you get 10 minutes. Okay? What else? I think that's pretty much it. What I recommend you spend this time with is learning how to use the multimeters perfectly and learning how to set up circuits. You can ask me anything you want from around. Okay? So take a break or start right away. Yeah. From capacitors and nothing required. So no flip follows and no electric. Yes.